Hello all, welcome back to yet another problem. Today let us solve the lead codes daily challenge, and the problem is find if path exists in graph. There is a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive, and the edges in the graph are represented as a 2D integer array edges where each edges of I equals to ui vi. It denotes a bidirectional edge between vertex ui and vertex vi. Okay, every vertex pair is connected by at most one edge. Okay, and no vertex has an edge by to itself. You want to determine if there is a valid path that exists from vertex source to vertex destination. So given the edges of integers n, source and destination, return true if there is a valid path from source to destination and or false otherwise. So actually we are given a graph and we want to find whether there is a path from source to destination. I hope the problem is quite understandable. Yeah. Okay, let us see the example. So if n is equals to 3, then the nodes are nothing but 0, 1 and 2, and the graph is going to be looking like this after we connect with these edges. So we want to find whether there is a path that exists between source to destination, which is 0 to 2. Yes, obviously there exists a path 0 to 2, so we return true. In the second example, as you can see, these are the two graphs. As you can see, they are two different components, but it is a single graph, and we want to verify whether there is a path between 0 to 5. And as you can see, 0 lies in one component and 5 lies in the other component, so definitely there is no path between them, so we can just return false. So how can we do this? Actually the constraints are 2 into 10 power 5, and this is the easy problem as well, easy tagged problem as well. We can just have a simple DFS from source to destination. We can just do a DFS on the nodes, and it is very quite simple whether to find whether there lies a path between them. I will in this video I'm going to solve this problem using DFS, and I'm going to give a new approach, another approach as well. How can we solve this problem if it is asked in interview? That is a good takeaway, I think, if we solve this problem using that. So let's do a quick DFS. How can we do a DFS? Obviously we'll go through all the nodes, and if it is not visited we will visit them, and we will check whether there is a path lies between the source to destination. So what we can do is we can first create a graph. Create a graph. So to create a graph, what we can do is we can have a vector of int graph of size n. Yeah, and now we want to map their edges. So for auto edge in my edges, how can we do this? Graph of edge of 0 dot push back of edge of 1. Similarly we can just put here in opposite way 0 and 1. That's it. Now we have created the graph. Now we can do a simple DFS. Return DFS graph. We can pass n. I think we don't want n. We can pass the source and we can pass the destination. And what we can do here is we also want a visited vector, else we will visit the nodes endlessly. So we can have vector of int visited of size n. We can have it as 0 initially, and we can pass this visited as well. Now we can have a function private. This is going to return me a bool, and vector of int graph of of size, it is a array, and we can have int source. Source is nothing but we let us depict it as u, because u is going to change, right? So if, and this is nothing but the destination, and we can have the vector of int visited as well. So now what is our base condition is going to be? The base condition is nothing but if my u is equals to destination, we are going to return true. So due to by this we can say we can say it is visitor, right? If it is already visited, if my current node visited of u is already visited, we can just return false, because we have not found any destination node. So this is another base condition. If it is not visited, or else we can take this line up. If visited of u is already visited, then we can just return false. If my u is equal to my destination node, then we can return true. Then we can just visit the current node. Visited of u is equals to true. Once we visited the node, what we want to go is we want to go and search in their adjacent nodes. So auto edge of my graph of u, what we can do is we can call the DFS function graph adjacent, and the destination stays the same, and visited. If this function is going to return me a true, then we can just return true. Else at the end of the day we can just return false, because we didn't find any path between the two nodes. Now let us try to run our code and see whether it gets passed in the two example test cases. Yes, it gets passed. So it is very simple, right? This is a DFS function, standard DFS function. We are creating a graph and we are calling this DFS function with the visit vector. Let us submit the code. So the time complexity here will be order of v plus e, where v will be the number of vertices and e is the number of edges. Superb, it gets accepted. So this is one approach. This is a standard approach that everybody gives. Let us solve this problem in different manner. I hope we can solve this problem using UnionFind. Why UnionFind is we can just reduce the time complexity by this. We can just add the edges between them, and if at all the source and destination is having the same parent, then we know that this source and destination is connected to the same component, and since it is in same component, it is having the same parent, and since it is having a same parent, there is a path exists between the source and destination. So this is the approach that we can do using UnionFind. And when we add these edges in our UnionFind data structure, disjoint set data structure, what happens is we are going to update their parents, and if it is going to belonging to same component, their parent is going to be same. So in such a way that we can prove that this a path exists between the source and destination if there is if there exists the same parent. So how can we do that? Let us quickly code the disjoint set union data structure. I will eliminate this code. I will say the class UnionFind. Here what I need is I need a parent vector and a rank vector. So vector of int parent and vector of int rank. I have two vectors now, parent and rank. I also need a constructor, right? So we can have a public UnionFind constructor. It takes a size n, and this is going to initialize parent the size of this resize of n, and rank dot resize of size n, and I'm going to run a for loop for int I equals to 0, I less than n, I plus plus. I am going to say the parent of I is I itself, and the rank of I is going to be 0 initially. So this is the constructor. Now we want to have two methods, which is the find parent and the union operation. So we can find first the find parent. We can define the find parent function. It takes a node u. If my u is equal to parent of u, then this is going to be my parent, so we can just return u. This is the base case. Else we want to do a path comparison. Parent of u is equals to find parent of u. So this is the find parent function. Now we want to do a operation. Yeah, void union. It takes two nodes int u and int p, and we want to find u is equal to find parent of u, and v is equals to find parent of p. Once we have find the original parent, if my u is equal to v, let us modify this union operation. No, okay, actually it is not needed. If my u is equals to v, then we can just return. Else what we want to do is we want to do a union between these two nodes. So what we have to do is if both is having the same parent, then we can just return. Else we want to do union between them. So how can we do the union? If my rank of u is less than or equals to rank of v, then what we want to do is we want to check if rank of u is equals to rank of v, then rank of v plus plus, and we want to say my parent of u is v, because rank of v is greater than rank of u, so we want to say parent of u is v. Else we can just say parent of v is u. This is what we can do in our union operation. Now we want to say we want to modify our union data structure based on this problem. We can have another method which is going to say, sir, we don't want this another method because we have already a find parent function. So this is going to return me this parent, what is the parent of that particular node. So instead of creating graph, we want to have a union find data structure object dsu of size n, and we can just traverse each edge in edges, and if we can create an edge first. How can we do that? dsu dot union of edge of 0 comma edge of 1. So by this we will be doing a union operation between those two nodes, since there lies a edge between them. And what we can do is, once we have created union, we can check for find parent, or else after doing all the edges we can just have a check here. dsu dot find parent of source is equals to dsu dot find parent of destination, then we can just return true, else we can just return false. So this is the proof, that is, if they lies in same component, their parent will be same, so that there exists a path between source and destination. Or else we can just do like this, return dsu dot find parent of source and equals to dsu dot find parent of destination. It is quite simpler, right? So this is our data structure and this is our main method, and it is very simple. And what will be the time complexity for this solution? Here the time complexity will be order of m, because we are just doing we are just adding the we are just doing a union operation between those edges, and if the m is going to be the size of these edges, then the time complexity will be order of m. And as you can see, this find parent, we are using a path comparison, So this is going to be not that much larger, and it is going to be a constant time operation since we will be doing a path compression. So yeah, let us try to run our code and check whether it gets accepted. Okay, actually, sorry, I need a semicolon here. Now let us try to run our code. Superb, it gets accepted. Great. Let us submit the code. Great. And as you can see, the DFS problem, the runtime is 1210 millisecond. But as you can see here, the runtime for UnionFind is 406 millisecond, which is very small than the DFS. And this is the code for this problem, and I hope you enjoyed this both approach. For this easy problem, it is better to know these data structures can be used very simple to solve this problem, solve these kind of problems. So let us see in tomorrow's lead code daily challenge. Until then, bye.